Hi, I'm Owen Traubert, and today I'm going to be talking about carbon dioxide showing a promising preclinical ability to prevent traumatic brain injury in mice. Traumatic brain injury, or TBI, is one of the leading causes of death and long-term disability worldwide. In 2014, there were nearly 3 million TBI-related deaths and hospitalizations in the United States alone. It can lead to secondary complications like Alzheimer's, Parkinson's, and chronic traumatic encephalopathy. It costs up to $15 billion each year and has been called the signature injury of the war in the Middle East. It's exceedingly common among athletes as well as laypeople due to accidents and falls. However, advances in helmet technology have failed to further reduce the incidence and severity of TBI due to coming up against practical design constraints. Therefore, novel therapeutic devices are urgently needed to address this public health crisis. So the most common type of TBI is mild TBI, also known as concussion. And what happens in a concussion is your brain rapidly accelerates and decelerates, slamming into the walls of the skull and causing all sorts of injury. The reason the brain is able to move so freely within the skull is an amount of tolerance known as the compensatory reserve volume. So within the skull, you have the brain, you have blood, and you have cerebrospinal fluid. However, there's a certain additional volume of fluid that can be added to the skull without increasing the intracranial pressure. Once you fill this volume, intracranial pressure starts to rise. So, if we could hold the brain in place more firmly by filling this space and thus increasing intracranial pressure, perhaps we could prevent the brain from impacting the walls of the skull. To illustrate this principle, on the right is a jar that is completely full, and on the left is a jar that has just a little bit of air in it. And as you can see, the egg on the right is having a much better time of things. So fortunately for us, there are numerous ways we can fill the compensatory reserve volume and thus alter the intracranial pressure. Something as simple as changing the angle of the head relative to the body can elicit significant changes in intracranial pressure. However, the most powerful and fastest way of altering intracranial pressure is increasing the amount of inhaled carbon dioxide. So when you inhale a higher than normal amount of carbon dioxide, your cerebral arteries dilate, causing increased blood flow to the brain, filling the compensatory reserve volume, and increasing the intracranial pressure. Therefore, due to this ability of carbon dioxide to fill the compensatory reserve volume, holding the brain in place more tightly, we hypothesize that treating mice with carbon dioxide before TBI will reduce the incidence and severity of the resulting injury because their brains are held in place more firmly and prevented from impacting the walls of the skull. To test this, we exposed mice to either 5% carbon dioxide or atmospheric air before exposing them to either blast or no blast for the control group. We measured body temperature at several time points relative to injury. Mice exposed to TBI display significant reductions in body temperature. We measured writing reflex time immediately after injury, and mice exposed to TBI display significant increases in writing reflex time. This is similar to coma scales in humans as a measure of consciousness. And 3 hours after injury, we measure locomotor activity, which is significantly reduced in mice exposed to TBI. However, mice exposed to a 5% carbon dioxide atmosphere for 10 minutes before TBI exposure had no alterations in body temperature compared to control mice, had no increases in writing reflex time compared to control mice, and had no deficits in locomotor activity compared to control mice. That is to say, these mice appear normal. Furthermore, because TBI elicits a miasma of gene expression changes, we wanted to see whether and how carbon dioxide could ameliorate these changes. We were able to identify 19 genes that are altered by TBI but prevented from alteration by exposure to carbon dioxide before injury. That is to say, these 19 genes represent the therapeutic targets of preventing the brain from impacting the walls of the skull. We have demonstrated that carbon dioxide, via its ability to increase cerebral blood flow, fill the compensatory reserve volume, and prevent the brain from impacting the walls of the skull, has a powerful ability to prevent TBI. Mice exposed to carbon dioxide before injury appeared physiologically and behaviorally normal, and many of the genes altered by TBI are normalized by carbon dioxide. We posit, therefore, that this principle can and should be developed into a preventative therapeutic for humans at high risk of TBI. Thank you for your time. Here are my references, and I'd be happy to answer any questions in the comments below.